So this one is a pipe flow, pipe, right? Normally if it's for liquid, so we call this geometry, these devices as pipe if the medium that flow through it is a liquid, right? So we can also use called tube. The device is called tube if the medium that flow through it as liquid, right? And we're going to call it different names. If it is gas, right, we're going to call it dark. If the medium is gas phase, so they are in gas phase and gas phase, right? So I think I hope you're clear with that. Now when we do this calculation in any engineering calculation, we're going to have an engineering assumption, right? So we have the engineering assumption, and for the fluid to flow in this system, we always assume that the fluid is incompressible, right? So what does this mean? So when we say fluid is incompressible, it means that the density is constant, right? Right. Normally, we assume water as incompressible fluid. Example of incompressible fluid. Uh, Water. So normally water is about 1000 kilogram per meter cube, right? So there is the density of the water. This um, can be the local density, can be also a density inside closed spaces, right? So let's say if we have a system in a closed thermodynamic systems, if we know the weight, the mass of the container, and we know the volume of the container, and from that we can calculate the density. Density of water locally at any point inside this domain, right? So let's say we have this location, right? So the density there is 1000 kilogram per meter cubic meters if it is water. And we have another fluid that is also depends on other variables such as air, right? For example, we have air. So air can be also assumed as a incompressible fluid. And for us to determine the air, we can assume that air behave like an ideal gas, or other name as perfect gas. And we can only calculate the density of air using the equation of state. Using the equation of state. Now, so we have the arrow here that represent velocity, right? Normally, here the arrow represent velocity vectors. So the velocity is defined by uh, symbol V. This one will be the fluid velocity, right? So this one is meter per second, right? So this one is meter per second. 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 Right Um, so we're going to use the standard notation here. We're going to use meters, we're going to use second, we're not going to use millimeter. If you have in meters, you have to convert to meters. It's easy, right? So this is the first thing that we have to do when we calculate the property of the fluid flow, right? And then another geometry that for this internal flow, right, is the cross-sectional areas, which is given by uh, A, right? A is the cross-sectional area, and this will be square meters, right? And then we have the volume flow rate. So this is our cross-sectional volume flow rate. Sorry, volume flow rate, and the unit will be cubic meters per second, right? Right. So this is the density. We have velocity. We have cross-sectional area, and then we have the volume flow rate. Next, we're going to look at the um, time rate of mass flow, right? If you look here, the mass flow rate represent the area here, mass that flow across the plane, right? If it is having same cross-sectional areas, or if not having the same cross-sectional areas, so the same amount of mass flow rate will be flowing to that direction, right? Amount of flow rate will be flowing into the domain, right? So we have mass here for PV, here the same value of mass, the same value of mass there.